All right, well, there's still algebra to go. So let's keep trying to write down each step for
So
algebra.
I divide by 4, and I can square both sides. So 1/16 equals 1 minus v squared c squared. And then, so we have 1/16 minus 16/16 equals negative 15/16 equals v squared. C squared, so v over c equals beta equals square root of 15/16. Okay.
Okay. What's our interpretation of this?
So 0.968 is how close you're going to the speed of light.
Are we going close?
Yeah.
So should relativity be important?
Yeah.
Yeah, this is pretty darn close. This is really fast, right? So this is almost the speed of light right here, way faster than normal speeds. Well, was relativity important here? How much was the length shrunk here?
1/4.
That's a huge shrinking, right? So we're getting a huge amount of shrinking, but you can see you gotta go really, really fast to get all that shrinking over there. Okay, so let's review so far. So first of all, there was one thing here we haven't talked about, which is that your instructor likes to talk about the speed parameter, I guess. So that's this guy here, v over c. Obviously, you'll have this formula in your notes. Now, when we looked at this a few weeks ago, as you were remembering, the key was to focus on which of these variables is the bigger and which of these variables is the smaller. Well, you can see from the equation, this has to be bigger because you're multiplying it by a fraction to get the smaller. And then we just had some trouble setting up the right algebraic equation here. So one thing that would have helped here is, I think that we were trying to plug in before writing down this equation. We were trying to substitute for one of the variables, but you cannot substitute for a variable until you know clearly what the equation is between them. So I think it was very tempting maybe to you to put the 4 over here. To put the 4 over here. And well, how can you figure out where to put it? Only by first writing down the equation that relates to variables before you do the substitution. First write down the equation before you do the substitution. Here's how we can kind of think through that. And notice, you don't really have to have ever studied relativity
To do this.
to get this right.
You pictures, you need to think about what
Right.
it plays. This is the easiest relativity problem.
That's right. It's really a math problem. It's a math problem. You never even have to have heard of rest length before. Because you can see, all you have to know is that the L's stand for length. And then clearly, since the rest length is the bigger one, the rest length must be L here. So there's no science here, it's just math. Okay. All right, and then we had some math hiccups as we went through this. So obviously you want to mark this question and go back and do it again. It's only with repetition that you can kind of iron out the common algebra problems that people have on these problems. Okay.
By what integer factor do the spaceship's clocks run slow compared to the clocks in the observer's frame? Okay, so this is a real response. So I want to use the. Should I draw pictures?
I don't think we need that here.
So I just want to use the t equation.
Yeah, we have to start by saying what is the t equation.
So the same thing.
Right.
T prime is t.
T times
1 minus v squared over c squared.
good.
So, oh wait, where did spaceship's clocks run slow? Oh, so we found what beta is.
Mm-hmm.
So we can put that in. So t prime equals t. So 1
Where'd you get the 0.968 from?
That's the answer to it. That's what, oh, no, never mind.
Yeah, what does the 0.968 represent?
That's what, V squared, V over C is. So if you do 0.968 squared,
Right.
squared, so you have 1 minus the square root of that. Six, right. Yeah, so T prime is, so the,
Now, let me see how you do that in your calculator. Let's go through that again.
so 0.968
Mm-hmm.
squared,
Right,
and 1 minus the answer,
good.
the square root of the answer. Should give us this.
Okay, okay, all right, keep going. Fine. I'm a little confused.
Maybe I'm on the reading. The clocks in the observer's frame.
You took the square root?
I think so.
I'll go back and type that again, sorry.
0.968 squared,
Right.
1 minus. What? Okay.
It looked like you were doing it right before, but that wasn't the right answer. I don't know what went wrong. I want to practice that, and I iron out that bug. They don't know what was going wrong there. Okay, so that's basically 0.25.
Yeah. So the spaceships on the clock go forward slower.
What was the question?
That's the spaceship. How, by what integer factor do the spaceship's clocks run slower compared to the clocks? By what integer factor? So integer means it has to be a whole number.
Right.
So by 4.
Pardon?
By 4.
Right. So it helps to make this into a fraction here now.
So T prime is the time on the spaceship.
T prime would be the time on the ground, which is
Oh, yeah.
smaller. If a clock is running slow, that means its time is longer. Now, if the clock is running slow, that means its time is, oh, let's try again. By what? Yeah, T prime, is that what you said? T prime is on the spaceship. Because this is the smaller number. When your time is running slow, you measure a short time.
Yeah.
And this is the longer time on the ground.
So since your time on the spaceship is, time feels shorter, then the time on the spaceship is T prime. No. Yeah, cause then it's the time on the ground, and if T is the bigger one, then it's T multiplied by some like fraction, or even, so T on the ground needs to become less to become T prime.
Right. Yeah, that's what I have written on the board now. Yeah, so they actually just told you in the problem that it's the spaceship's clocks that run slow. They told us in the problem that the spaceship's clocks run slow. They didn't even require us to use relativity to figure that out. Well, we know that if your clocks run slow, then you measure short times.
Yeah.
So this must be the time of the spaceship. Now, so by what factor did the two times differ? And by what time do the two lengths differ?
But 4.
And that's no coincidence, because the equations are exactly the same.
Yeah.
We didn't have to do any of this work. We didn't have to do any of this work. They both have this square root term in them. They both have to differ by the same factor. Both of these have to differ by the same factor because they both have the same square root term in them. So the relationship between the ratio of the integer difference, factor difference between the lengths is always going to be the same as the difference between the times, because they both have the square root term in them.